Hello everyone. This is Krish this side, and today we'll be discussing about ARIMA. So before we move forward, let me give you a brief about me. So that is me. So I've got around 9.6 years of experience, which ranges from data analytics, market research, machine learning, deep learning, and a bit of consulting. The models which I've created include like RFM, early sensor frequency monitoring models, customer lifetime value, customer 360, churn model, machine learning APIs, deep learning solutions, recommendation systems, risk models, credit score limits, and NLP, sentiment analysis, are some of the things which I have prepared, and some of the tools which I've got a competency with are SQL, Python, R. I started with SPSS, and these are the tools which I have till now. Okay, now let's move to ARIMA, today's topic of discussion. So, when we talk about ARIMA, it's important for us to understand some a few requisites, like what is time series. Let's talk about what is time series. Time series is something which is based on time. When I say time, it can mean years, months, weeks, days, minutes, or even seconds. When we have data which is based on different equal intervals of time, we call that a time series. And based on that time series data, we can forecast or predict the future. Okay, now, so how it is done? So we know what is time series. So what it does, uh, we have the historical trend or the previous data which has occurred over the time, and we study that, analyze it, and based on that, we forecast the future events. Okay, we have been talking about forecasting, but it is a bit tricky term. Okay, forecast means when we are predicting the future, but and it is based on time, we say we are forecasting. And prediction is something when we for predicting something which is forecasting the future, or predicting the future. That is forecast. The only difference between forecast and prediction is forecast is based on time, and prediction doesn't depend on anything. Okay, and we can say also like forecast is a of subset of prediction. So if you see the two graphs, okay, the first graph is the forecasting thing. So since because it is based on time, which will give you a discrete number, and based on forecast, we cannot do any classification or doesn't give any categorical variable in return. But in prediction, we also get a discrete variable, a value in return, but it is not based on time. That's the only difference between forecast and prediction. Although they mean similar things, but there's a difference. When it is time involved, it's called forecast. Otherwise, it's prediction. Okay, now we'll know a little bit like what are the forecasting techniques that are there. Okay, there are two techniques we can go ahead for the forecasting. One is time series and the other is regression. When we are dealing with time series, we mean we are dealing with univariate analysis. By univariate, we mean we have just one data point, or one variable, and based on which we can go about for the forecasting. And here we will be studying about ARIMA. But for regression, we can do bivariate analysis and also univariate analysis. And for that, we can go with regression. And like in regression, we talk about multiple linear regression. We can build a random forest regression model. So there are different models which you can build using the regression techniques, which will give you again both. In both the cases, you will get a discrete numbers. Only thing is in ARIMA, it is based on time. Okay, so we have been talking about ARIMA. So it is important for us to understand like what is ARIMA and what it is used and what is the purpose and how is this used. So those are things which are going to cover in the next slides. Okay, ARIMA is one statistical technique which is used for the time series forecasting, or based on time we forecast the future. ARIMA, as the term ARIMA, it stands for autoregressive integrated moving average. It consists of three components. Okay, so there are different types of ARIMA models which we have, like moving average, ARMA, where here auto-regressive moving average model, auto-regressive integrated moving average model, or moving average model, additive model, exponential model, auto-regressive fractional integrated moving average model, seasonal auto-regressive integrated moving average model. So these are all the types of ARIMA models which is available. But what we generally most commonly use is this ARIMA model. Okay, as I told you, like ARIMA consists of three components. Okay, autoregressive, integrated, and moving average. What is this autoregressive term? Or in autoregressive, there is a lag term which is there. It is based on the dependent variable based on which the lags are created. Integrated. When we talk about integrated, it's the difference based on the original variable which we get, and moving average is between the residual based on the residual error. So these are three of the components based on which the ARIMA model is based. For auto, and it is, and those components are denoted by, like, auto regressive is defined by P, integrated by D, and moving average is defined by Q. And these are all the parameters which comprise the ARIMA model. And the ARIMA model is defined or denoted by ARIMA bracket P D Q, where P is autoregressive term, D is the integrated or the difference, and Q is the error moving average or the error term. Okay. Okay. Now moving to the next slide. Whenever we build ARIMA model, it's these things P, D, and Q are the parameters based on which the entire model is dependent. Like P, we call the lag order, number of lag observation that is included in the model. D is the difference, like what's the difference that you're going to take, or number of times from the raw data or the transform data that you're going to take. And Q is the moving average, the size of the window that you're going to take. And all these P, D, and Q are discrete numbers, and they normally range from 0 to like 2, 3, 4. And like in statistically, we normally take from 0 to 2. So, and the model is defined like ARIMA of order. If I write P, D, Q, P equals to 1, D equals to 0, and Q equals to 1, I will write as ARIMA 1, 0, 1. So that's how it is denoted. Okay, we have understood, like, the ARIMA model consists of these three parameters. But what do we do with these things? What this algorithm does is, based on these three parameters, is create a regression model. And based on these regression model, they forecast the future trends or the future values after removing some of the components. By components, I talk about trend, seasonality from the data which is present in the data. When we get data, okay, based on time, it involved a lot of components which are going to cover in the next thing. Okay, in the next slide. Okay, in this slide. So when we talk about time series data, it involves a lot of components. These four components, like trend, seasonality, cyclic or irregular component, and our objective of this building the model is we have to get rid of all these four components and then build the model. And if we include all, and if you build an ARIMA model and these are there, like, your model won't give you a good prediction. Trend is something which is for a short duration. Seasonality is something which occurs over a period of time. Cyclic is something which occurs after some intervals. An irregular component that just occurs and they not have any pattern for that. It's like based on the okay, sorry. It's like based on different based on these things, you have to get rid of this so that your model is stationary, and then you can go ahead build the model. Okay, now let us understand how this ARIMA model is built. As I told you, like there are ways in which you can build the model, but here we'll be considering the univariate data. By univariate, I mean you have just one variable. Okay, and based on which you are going to do, so your data will consist of 2 points. One is the time factor, and the other is the y, that is your data, that is univariate. So what you have to do, once you get the data, you have to group it, or you have to have the data based on time, and also you might have to make sure that the time factor is unique in each of the records. Like it might occur, like if you are fetching data from different tables, there might be cases on the single day you have couple of if you are taking if you talk about sales data, you might want to say one particular day there might have couple of records. So it would be great if you take the aggregate of those sales data and then move about building the model. So once you group the data based on time, the next thing you have to do is make the data stationary. For making and for that you have to remove all these four components like trend, seasonality, cyclic, and irregular component. And there's a test which tells you like whether your data is stationary or not, that is using the Dickey-Fuller test. Okay, after that is done, the next is you have to build the model based on with those three parameters, P, D, and Q. And those parameters are defined based on two analysis like ACF and PSF. Okay, and which are going to cover in the next slides. Okay, so we understood like how, or we have an idea now like how the ARIMA model is built. So let us understand like for when we are building model, for what it is used. Like ARIMA model is used for a lot of forecasting, or it is highly helpful for the leaders to make decisions for the better growth of their organizations. Like for example, I am a sales manager. So if I get the forecast for the next 6 months, I will understand like how my team is progressing. If there is a decline, I will take steps so that the sales figure doesn't go down. So for weather forecast, we know like for the next 7 days what the weather is going to be, if there is any flood or not. So I will take some precautions for that. So these are some of the things, some of the cases where ARIMA is used for the forecasting, like stock market prediction, exchange rate, revenue forecast, weather, sales forecast. These are some of the things. There are plenty of cases where forecasting is used using the ARIMA model. Okay, these were there is a few more techniques which are advanced, and they give you better predictions than the ARIMA model. Like if I talk about LSTM, which is based on neural network, long short term memory. So LSTM we use for the stock market prediction, and they give you better forecast. And there is another algorithm or library which is available from the Facebook, which is they have developed, is a Profit. And this algorithm, they take into consideration the holiday factor as well. Like suppose you are predicting on a daily basis the sales forecast, and in case there are some holidays or national holidays, this algorithm is going to consider that as well. So these are the some of the some complex algorithm apart from the ARIMA model. Okay, now let us understand like how we go about building the ARIMA model. So, so first is data collection, step one. So whenever you are at type like for any problem, you are predicting the sales, you are predicting the weather, you are predicting the revenue. So for that, you must have that data. Once you get the data based on time, you're going to group that data so that it becomes on a based on you get that data based on the time that you're looking for. Suppose you got the data on a daily basis. Now suppose you want to predict it on a monthly basis, you have to convert it from a daily to on a monthly basis, and then go about predicting. The next thing is, once you have grouped the data, or you have obtained it from different sources, you import the data into the Python environment. So once that is done, next comes the pre-processing steps. In pre-processing, there might be um, different issues that you must face. Like your data might contain some outliers. Okay, outlier is something like which falls beyond your control limits, like upper control and lower control. Or if I take in a layman term, is an outlier is something which falls beyond the normal, beyond the data that is available. Like for example, you have let's take about scores. The scores might range from 0 to 100. Like 0 is your lower control and 100 is your upper control. Like suppose you get any data point which is say telling 1000. Like 1000 is something which is beyond the ordinary, and it also falls beyond the control limit. So we'll term that as an outlier. So in this step, we are going to get rid of in this step we are going to get rid of the outliers. The next thing is you have to check whether there's any missing values or not. By missing values, I mean like there might be cases for a certain day there is no data available, and and um, um, and you are predicting on a daily basis, on a monthly basis. So it would be better if you impute the data. By imputation, I mean like if there is any missing value, data is not available, you could just replace it with you can replace it with the next value, or the previous value, or the average value, or the mean value, based on your decision, whatever you want to impute it with. So that completes your pre-processing. Okay, I forgot to mention one thing. Okay, so once your data is doesn't contain any outlier, doesn't contain any missing values, the next is you have to transform the data. I say like why you have to transform the data is because the objective is you have to make your data stationary. So for making that data stationary, you have to transform your data. Otherwise, it will be very difficult for the ARIMA model to process. Like the most common transformations are log scale, which logarithmic scale. So you convert your data into log scale. There are you can take the square root of it. You can take the cube root of it. Even like you can take the cube root of the square root of that value. Like based on the transformation which you're comfortable with, you can go ahead with that data. So that completes your pre-processing steps. Okay, the next is if you want to find out some descriptive statistics or respiratory data analysis that you're going to do, so you can go ahead with that. Like finding out this gives you an idea like what's the data, what's the variation, what's the trend that's going there. Okay, so based on different graphs that you're going to do, similarity trends that you can see, you can figure out what's your data is about. Okay, and also you can calculate the moving average based on different time periods. The next is making your data stationary. So for that you have to remove those four components like trend, seasonality, and irregularity. So there are different ways in which you can make your data stationary. So you have already transformed your data. You can take the difference from the original data, shift the scales, and then check for the use Dickey-Fuller test for stationarity. And what is this Dickey-Fuller test? Dickey-Fuller test is one test which tells you whether your data contains all these four components or not. And how it is defined? It is based on the p-value. P, as you know, the level of significance. If it is less than 5%, you can say like your data doesn't contain any. Your data is stationary. The next is you're splitting your train and test data. So splitting of this data is a bit tricky. I When I said tricky is that when you are building any other models, like we are considering a classification model or any regression model, in that case when you split the data, you split it based on ratios, and here also you're going to split it based on ratio. But here one thing you have to consider is based on your time period, since you are dealing with time. Suppose you are considering say 2 3 years of data you're considering, and you're analyzing it based on a monthly basis. Okay, what you can do is you can take the 2.5 years of data and put it in your train data, and take the last 6 months as your test data. So that is how it is done if you are doing it in a daily basis. So you can take the 2 years you can take For 3 years data, you can take again. You can take like 2.5 years of data and put the 6 months as your test data. This is how you can go about it. Okay. So for next is finding out what are the parameters of the model. Okay, so there are as I told you, as we had discussed, there are three parameters: P, D, and Q. So P, D, and Q, you have to get the model and then build the model. So for finding out what are the three parameters, you have to do the SCF and PSCF analysis for finding out the model parameters. And the next comes building the model. So you know your data is stationary. Okay, you know the three parameters. Now you are going to, based on your trained data, you're going to build the model, then test the model, check for RMSE, MSE, and EIC score. So once you're satisfied with it, you can also take one more step in validation of the model. Validation is something uh, which is uh, which is an additional step which is taken for finding out whether your model has been built properly or not, or whether the model is able to predict accurate values or not. Okay, since in time series there are only a few tests which are available for the testing whether a model is good or not, good fit or not. Okay, so for that, what you can do is, suppose you are taking 3 years of data. So what you can do, you can take 2.5 years of data, build the train set. Okay, then take the last 4 months as your test set and the last 2 months for your validation set. And also you must have to keep in mind, like it shouldn't be like, if there is a, suppose suppose you have got you're considering 10 years of data, and that is you're predicting on a daily basis. The more data or the more data points you have, uh, the model will get more time or more data to train, to get have got more data to train itself. And based on the more your data you give, the more better your model will predict in future, because the more data it will come, the more training it will get, and the better it will predict. So since machine learning is all about getting more data. If you have got less data, then there are a few chances that your model won't work properly. So that's how we build the model. Okay. The next thing we must find out, like, so we talked about how the model is built. We know the parameters. We know the components. So when we are building the model in a Python environment, we must know, like, what are the libraries that are available for, what are the libraries that is required. So NumPy is one thing which is required. NumPy, Pandas, Matplotlib, and Stats model. So these are the four libraries that are required for building your ARIMA model. And in Stats model, it will cover all of the libraries or small libraries that are required in the model. Now we'll talk about a case study. Okay, so in this model, we are giving sales data, which comprises of 6 years of data, and this data is already on a. I think it's on a. We have the model based on time, and what you're going to do, you're going to train the 5.5 years of data as your train set, and the rest 6 months for the test set. So what is going to help? Goal of the model or goal of the study? This is going to forecast the future sales for the next 6 years, 6 months. Okay, and this will help the leadership to take decisions whether they have to take some more steps for the agents to work on, or they are what it will give you an idea like at what stage they are in. Okay, now we'll be moving to the Python environment. First thing first, we have to import these libraries like Pandas, Matplotlib, Stats Model, as I told you, like ADFuller, ACF, PSCF, and the ARIMA. These are some of the libraries which are going to import. The next comes is importing your data. So OS is for changing the directory. So this is one of the libraries which is available. Okay. The next thing is you have to group that data which I have done using the index function based on time, and which is done on a monthly basis. and here the sales data is the loan amount, which I've grouped on a monthly manner. So if you see it, the data that was available was on a daily basis, which I've indexed it, which I've grouped it in a monthly manner. Okay, now if we plot in the table, if we plot the data on a, like, we take X as a date and Y as the sales. So this is the figure that you are going to get. So we see what from the graph, what we can see is we can see a incline in the sales over the years. Like 2013 to 2018, there is a gradual rise, and we can see in certain duration there is a seasonality is there. Like here, and here, there's a spike up and there is a spike down. So from the graph itself, we can see that your data is not stationary. So for that we can have your Dickey-Fuller test, and it will give you the same results. So I've taken the just find out the moving average on a 3 month basis, which is available. So that's just for extra which I've done. Okay. Okay. Now move to Dickey-Fuller test. This is a model which I've done earlier, for that we won't be talking about, but coming to the Dickey-Fuller test. So so this is the function which is available. We are plotting the Dickey-Fuller test. Also, one thing which I missed out. Okay. Just a minute. Okay. No, that's fine. So this is the thing we have. Okay, so we have just run the Dickey-Fuller test. So as you see from the graph, from these values, the p-value is coming to 1. So we can say that your data is not stationary, and because the p-value is coming to 1, which should be less than 5% or less than 0.05. Okay, so now comes the data transformation. As I told you, so X was the sales figure, so which we have. I mean X. Okay, no, this might be some mistake. I figured. Okay, so what I have done is I have taken the cube root first, and then taken the square root of that cube root. Okay. So what I have done in this transformation, I have taken the square root of the cube root of the sales figure. And again, you can see the graph. If I plot it on a time basis, I will get the same type of graph which was available earlier. So that is based on after the transformation, the graph or the trend doesn't change a lot. And you can see if I just listed out the Y transformation which I've done, it will give you the sales figures of the transformed. Okay, now here I have taken the moving average and plotted it on the graph. So here also I have taken the 3 months figure. Now the next thing is, since we talked about like transformation, we did not get a good result because the Dickey-Fuller because it was not coming to stationary. So what we have done, we have taken the difference from the transformation and the moving average. So this is the after taking the difference, this is the again transform data that you are getting. And again, we are running the Dickey-Fuller test, and let's see. This is the plot that is available from the graph. Before moving to the uh, values, let us see what the graph talks about. Okay, if you can see, like in our previous graph, we have seen there is an incline. But if you see the data, the graph that is the original data, which is the transform data, if you see that is the original data, something like based on the difference that we have taken, it is fluctuating on in an interval which has become flat. Okay, so which is we can at the back of the mind, it's telling like yeah, we are in the right path. Okay, and also your rolling standard deviation is something which is also in the same which is also falling in the same trend. It's the same trend that is catching. So we can say like we are expecting some good results. Let us see what's the p-value says. Okay, the p-value we are getting something 0.004584, and which is uh, which is less than 5%, and we can say your data is now stationary. Okay, now we have to find out the different trends that is available in the data, like residual, rolling mean. These are some of the graphs or the different components as I talked about, like trend, seasonality, irregular components, which is available. It's for descriptive statistics. Okay, now come the main part, that is ACF and PACF. ACF stands for autocorrelation factor and PACF stands for partial autocorrelation factors. If you want to know more about this, it is available, but as of now, that is not required. Okay, how PACF and ASCF and why is it required? Okay, so here I have taken the lag as 10, and based on which I have I have found out the ACF and PACF. So this is the graph of ACF. Okay, what does this graph signify? The objective of this autocorrelation function or this graph is to find out whether this line touches 0. Okay, so that is will be one of the um, parameters of the model. If you see that this in ACF, the line touches 0 and we can say close to 1. So 1 will be the border of the ARIMA model. Now let's plot the PACF graph. And again, you can closely seen like the line touches 0 in again 1. Okay, so we can say we can go ahead with the parameters of 1 1, and what we have done is also we have taken the order of 2 1 1. It's just because like it's like it's the final result which I've got. You can try out with 0 1 1 1 1 1 1 or ARIMA 1 1 1 or ARIMA 2 1 1 1. This is the best result which I've obtained after some 2 3 iterations. The only disadvantage of ARIMA model is it's like it requires a lot of human intervention, and also like you have to like trial and error you have to do. You do not have any libraries which will or function which will give you the result. Okay, this is the thing that you're going to use. Based on the graph I have obtained two of the parameters, but still I was uh, based on the model and the values that I was getting, I was not satisfied with it. So after predicting, after trying out different combination, this is the model which I got the result. So if you see, RSS is coming to 1.76, which is quite high. Based on the data that is available, the data based on the seasonality of the data, based on the trend of the data, I have seen like in 2013, 14, and 15, in the first 3 years, the data was not that complete, and where it was not, if you talk about in statistical term, it was not normalized or standardized. And if in the last 2 to 3 years, the values are quite high. In the first 3 years, the day values were quite low, because of which we see the RSS coming to be quite high. You must always make sure that your RSS comes to below 1. The lesser it comes, the better is your model. Okay, so I've tried out different combinations as I told you. So this is the final model which I have got. Now what I've done, I have predicted for the next 91 interval. I mean the 91. I mean like the number of like first month, second month, third month. So that's how I have predicted. This is the forecasted figure, and this is the original, the orange one. Okay, so that is your forecast, and this is the figures, the values of the predicted figure. So that's how I will say like my model that I've created is not that much great, because if you see, um, your model, your predicted value must come to like this. If you see the blue line, you'll see like your data, your trend line, the predicted values are not that it doesn't contain any seasonality or any kind of pattern. That wise you see a smooth line that is coming up. But in your original, like there is ups and downs, there is a in different intervals you're getting high and low. So and that's how your forecasted is predicted. But now if you want to make it to your original data, you can put in your seasonality in place, and then you'll get a crooked line based on the original data. Okay, So that's what, like in this, the predictor line doesn't contain any seasonality, so you get a smooth. Otherwise, if you want uh, the seasonality in place, that's our orange data. So that's all from the Python part.